Hi, so here I am in my home office, and I thought I would do a quick recording here of our, or re-recording of our in-class discussion about how evolution can lead to antibiotic resistance. So I'm going to do that on my iPad. The video feed will disappear because Camtasia won't take a camera input while it's recording an iPad. So in a few moments you'll see my iPad appear, and we'll get going with our description of how antibiotic resistance can arise due to evolution by natural selection. So I'll start that in a moment. So let's talk about how evolution by natural selection can lead to antibiotic resistance. So here's Stewie. We did Steve in class. This is Stewie. Some of you recognize Stewie. And Stewie's got a chest infection, so infection in his lungs. And his folks, surprisingly, have taken him to the doctors, and he's got a course of antibiotics. And his parents have been told that Stewie's got to take his antibiotics 3 times a day for 10 days. That's what his prescription says. So, as Stewie's lungs, we're going to think about Stewie's lungs here as kind of hosting a population of bacteria. And so in this population of bacteria, there's going to be just some natural variation. And the variation we're interested in is in a gene which gives the antibiotic, gives the bacteria the ability to resist a certain antibiotic. It doesn't matter, we can pick any antibiotic. So there are some green bacteria, and these green bacteria have a variation of the allele which just makes them, normally sensitive to the antibiotic that Stewie's taken. But then there are some bacteria in the population which, just because of DNA replication and random genetic change, have a variation of this resistance gene which makes the bacteria much more resistant to the antibiotics Stewie's taking. And then we're going to put in some red bacteria to this population, and these bacteria are going to be highly resistant to the antibiotic that Stewie's taken. So that's the variation in the population that we talked about before, that is a requirement for evolution by natural selection. So Stewie starts taking his antibiotic, and he takes it for a few days, and that eliminates these sensitive bacteria, the ones that don't have really any resistance at all to the antibiotic. And so those bacteria all get killed off, which is great. Stewie starts to feel a little better. He keeps taking the antibiotic, and then after maybe 6 or 7 days, all of the bacteria which are slightly resistant, not completely resistant, but slightly more resistant than the green bacteria, they get killed off as well, just because they've been exposed to the antibiotic longer, and that leads to them getting killed. And then Stewie keeps taking his antibiotic, and maybe he's up to like day 8, and he's even been able to kill some of these more resistant bacteria. But he gets to kind of day 9 of his treatment, and his folks see that he's looking a lot better, and he's up and about and zapping people with his ray gun. And so they stop giving him his antibiotic. And as soon as you remove that pressure that is killing these bacteria, the bacteria can start replicating again. And so all that's left are these resistant bacteria. And so now all these resistant bacteria start to take over in Stewie's lung, and he gets sick again. And so as these bacteria keep dividing, they have to replicate their DNA so that they can grow and divide. And as that occurs, there are just more mutations. DNA replication, although it's very, very accurate, there are occasionally mutations. And so every now and then a mutation will arise, and it's going to create a superbacterium or a superbug that's even more resistant to the antibiotic that Stewie's taken. And so a few of those bacteria arise, and Stewie's back at the doctor at this point. He's got another course of antibiotics. He starts taking his antibiotics, and he's taken it for full 10 days, and that's great because he's killed all of these really resistant bacteria from before. But this antibiotic just cannot cope with these new superbugs which have appeared. And so even though Stewie's taken as antibiotic, doesn't have any effect on this population. And so we've got a new population that have appeared, which are completely resistant to Stewie's antibiotic and possibly even to other antibiotics that Stewie could be given. So if we think about this in terms of our definition of evolution, which is a change in allele frequency, so remember we can say a change delta. So delta, remember, stands for change. So a change in allele frequency, basically as a function of time. And we can ask ourselves, can we apply this definition to this phenomena which I've just described here? So let's think about the allele frequency to start with, and then see if there was a change in allele frequency. So see if this situation aligns with that part of our definition. So remember, we started off with some really sensitive bacteria and some kind of intermediately resistant, that's a word, intermediate resistance bacteria, and then we got we had some much more resistant bacteria. Now you've got to think about the fact that there'll be billions and billions of these bacteria. So there'll be billions of the green ones, billions of the blue ones with their gene variant, and billions of the red one with their gene variant. And so there would be a frequency of alleles. So maybe there were 5 billion of the red alleles and 7 billion of the blue ones and 12 billion of the green ones. That's a certain frequency and a certain ratio of the alleles. And so we started off with a certain ratio, and we're just going to say, okay, that the frequency of the green was X, the frequency of the blue was Y, and the frequency of the red was Z. And so our ratio is kind of, you know, or it's X to Y to Z, and that's what we started with. But well, then along came the antibiotic, and it eliminated the green and it eliminated the blue, and all we were left with then was the red. So all we had left was the red. So we went from this kind of frequency or this distribution of the alleles to just 100%. Every bacteria basically had this allele of the gene which conferred antibiotic resistance. And then remember, when Stewie kind of stopped taking the antibiotics and this red population of bacteria are allowed to proliferate, is what happened is we went from 100% of the red, what we just call Z, we went to 100% of the bacterium with this new allele. We'll just call it the black allele, and we'll call it Q. And so the allele frequency changed again. And so let's get the right razor. And so it changed again. So yeah, there was definitely a change in the allele frequency. So let's now look at this function of time business. The time factor here is each generation of the bacteria. And so every time a bacteria divides, that's a generation. And for the garden variety Escherichia coli that you find in your intestines and in water supplies and things like that, it can be as short as 20 minutes. So bacteria can test out new mutations very, very frequently and very, very rapidly, whereas you or I, our generation time is basically from birth until reproductive maturity, whenever that would be. And so that's why we can't keep up with this arms race effectively with antibiotic resistance in bacteria. So there's definitely a change in allele frequency as a function of time. And the last part of our definition had to do with it being in a population. Now, it's easy to think about populations in terms of macro kind of organisms. In the classroom, we could have a population of humans. You could go into a forest and find a population of birch trees, for example. The population here is the group of bacteria in Stewie's lungs. Now, they're not a population in the sense that they can interbreed, but they are going to be the same species. They can share genetic material, and so for our purposes, that's the population. So this example meets all the criteria we have for evolution, and the mechanism of evolution here is natural selection. In general biology 2, you'll talk a lot more about different types of mechanism for evolution, and you'll talk about gene drift, genetic drift, and gene flow, and also more about natural selection. So that's how we can get antibiotic resistance in bacteria as a consequence of evolution by natural selection. I will see you next time. That's all for now.